Warmest greetings to all my incredible subscribers and new viewers alike. Welcome, curious minds, to our video that explores the ins and outs of Cohen-Macaulay ring. In mathematics, a Cohen-Macaulay ring is a commutative ring with some of the algebro-geometric properties of a smooth variety, such as local equidimensionality. Under mild assumptions, a local ring is Cohen-Macaulay exactly when it is a finitely generated free module over a regular local subring. Cohen-Macaulay rings play a central role in commutative algebra. They form a very broad class, and yet they are well understood in many ways. They are named for who proved the unmixedness theorem for polynomial rings, and for who proved the unmixedness theorem for formal power series rings. All Cohen-Macaulay rings have the unmixedness property. For Noetherian local rings, there is the following chain of inclusions. As we enter this new phase, let's analyze definition from different angles and evaluate its significance. For a commutative Noetherian local ring R, a finite i.e. finitely generated R module M0 is a Cohen-Macaulay module if depth-dim. In general we have depth-dim. See a Slander-Buxbaum formula for the relation between depth and dim of a certain kind of modules. On the other hand, R is a module on itself, so we call R a Cohen-Macaulay ring if it is a Cohen-Macaulay module as an R module. A maximal Cohen-Macaulay module is a Cohen-Macaulay module M such that dim-dim. The above definition was for a Noetherian local rings, but we can expand the definition for a more general Noetherian ring. If R is a commutative Noetherian ring, then an R module M is called Cohen-Macaulay module if MM is a Cohen-Macaulay module for all maximal ideals M sub. This is a kind of circular definition unless we define zero modules as Cohen-Macaulay. So we define zero modules as Cohen-Macaulay modules in this definition. Now, to define maximal Cohen-Macaulay modules for these rings, we require that MM to be such an RM module for each maximal ideal meters of R as in the local case. R is a Cohen-Macaulay ring if it is a Cohen-Macaulay module as an R module on itself. With our curiosity piqued, let's embark on a dedicated exploration of examples and its fascinating intricacies. Noetherian rings of the following types are Cohen-Macaulay any regular local ring. This leads to various examples of Cohen-Macaulay rings, such as the integers z, or a polynomial ring Kelvin over a field K, or a power series ring K. In geometric terms, every regular scheme, for example a smooth variety over a field, is Cohen-Macaulay. Any zero-dimensional ring or equivalently, any Artinian ring. Any one-dimensional reduced ring, for example any one-dimensional domain. Any two-dimensional normal ring. Any Gorenstein ring. In particular, any complete intersection ring. The ring of invariance reg when R is a Cohen-Macaulay algebra over a field of characteristics 0 and G is a finite group or more generally, a linear algebraic group whose identity component is reductive. This is the Hochster-Robert theorem. Any determinantal ring, that is, let R be the quotient of a regular local ring south by the ideal I generated by the R minors of some PQ matrix of elements of south. If the codimension or height of I is equal to the expected codimension per R is called a determinantal ring. In that case, R is Cohen-Macaulay. Similarly, coordinate rings of determinantal varieties are Cohen-Macaulay. Some more examples. 1. The ring Cox has dimension 0 and hence is Cohen-Macaulay, but it is not reduced and therefore not regular. 2. The subring Kelvin of the polynomial ring K, or its localization or completion at, is a one-dimensional domain which is Gorenstein, and hence Cohen-Macaulay, but not regular. This ring can also be described as the coordinate ring of the cuspidal cubic curve I equals over Kelvin. 3. The subring Kelvin of the polynomial ring K, or its localization or completion at, is a one-dimensional domain which is Cohen-Macaulay but not Gorenstein. Rational singularities over a field of characteristics 0 are Cohen-Macaulay. Toric varieties over any field are Cohen-Macaulay. The minimal model program makes prominent use of varieties with comatolog terminal singularities, In characteristic 0, these are rational singularities and hence are Cohen-Macaulay. One successful analog of rational singularities in positive characteristic is the notion of f-rational singularities. Again, such singularities are Cohen-Macaulay. Let X be a projective variety of dimension n1 over a field, and let L be an ample line bundle on X, then the section ring of L. Our J-shocks is Cohen-Macaulay if and only if the cohomology group X is 0 for all one ein and all integers j. It follows, for example, that the affine Cohen spec R over an abelian variety X is Cohen-Macaulay when X has dimension 1, but not when X has dimension at least 2 because Hox O is not 0. See also generalized Cohen-Macaulay ring. With our foundation established, it's time to explore Cohen-Macaulay schemes and its relevance to our overarching theme. We say that a locally Noetherian scheme X is Cohen-Macaulay if at each point X the local ring X is Cohen-Macaulay. In the next phase, we'll be immersing ourselves in the realm of Cohen-Macaulay curves and exploring its real-world applications. Cohen-Macaulay curves are a special case of Cohen-Macaulay schemes, but are useful for compactifying moduli spaces of curves where the boundary of the smooth locus G is of Cohen-Macaulay curves. There is a useful criterion for deciding whether or not curves are Cohen-Macaulay. Schemes of dimension 1 are Cohen-Macaulay if and only if they have no embedded primes. The singularities present in Cohen-Macaulay curves can be classified completely by looking at the plane curve case. As we venture forward, let's examine non-examples in detail and gain a deeper appreciation for its significance. Using the criterion, there are easy examples of non-Cohen-Macaulay curves from constructing curves with embedded points. For example, the scheme X a text spec left frac-complex X I right has the decomposition into prime ideals XX, Y. Geometrically, it is the y-axis with an embedded point at the origin, which can be thought of as a fat point. Given a smooth projective plane curve C, a curve with an embedded point can be constructed using the same technique. Find the ideal Ix of a point in XC and multiply it with the ideal IC of Celsius. Then, X a text deproj left frac-complete Z got X right is a curve with an embedded point at X. In this section, we'll be exploring intersection theory. Cohen-Macaulay schemes have a special relation with intersection theory. Precisely, let X be a smooth variety and V, W closed subschemes of pure dimension. Let Z be a proper component of the scheme theoretic intersection V XAU, that is, an irreducible component of expected dimension. If the local ring of V XAU at the generic point of Z is Cohen-Macaulay, then the intersection multiplicity of V and W along Z is given as the length of a is VW, X length a. In general, that multiplicity is given as a length essentially characterizes Cohen-Macaulay ring C properties. Multiplicity 1 criterion, on the other hand, roughly characterizes a regular local ring as a local ring of multiplicity 1. Brace yourself for an in-depth analysis as we navigate through example and its far-reaching implications. For a simple example, if we take the intersection of a parabola with a line tangent to it, the local ring at the intersection point is isomorphic to a frac-complex XO times complex frac-complex psychon frac-complex X, which is Cohen-Macaulay of length 2, hence the intersection multiplicity is 2, as expected. Get ready for an exciting exploration as we unravel the mysteries of miracle flatness or Heronika's criterion. There is a remarkable characterization of Cohen-Macaulay rings, sometimes called miracle flatness or Heronika's criterion. Let R be a local ring which is finitely generated as a module over some regular local ring contained in R. Such a subring exists for any localization R at a prime ideal of a finitely generated algebra over a field. By the Noetherian normalization lemma, it also exists when R is complete and contains a field, or when R is a complete domain. Then R is Cohen-Macaulay if and only if it is flat as an A module. It is also equivalent to say that R is free as an A module. A geometric reformulation is as follows. Let X be a connected affine scheme of finite type over a field Kelvin, for example, an affine variety. Let n be the dimension of X by Noether normalization. There is a finite morphism f from X to affine space and over Kelvin. Then X is Cohen-Macaulay if and only if all fibers of f have the same degree. It is striking that this property is independent of the choice of f. Finally, there is a version of miracle flatness for graded rings. Let R be a finitely generated commutative graded algebra over a field K. Archera. There is always a graded polynomial subring at R with generators in various degrees such that R is finitely generated as an module. Then R is Cohen-Macaulay if and only if R is free as a graded module. Again, it follows that this freeness is independent of the choice of the polynomial subring A. Now, let's shift our perspective and explore properties from a different angle. A Noetherian local ring is Cohen-Macaulay if and only if its completion is Cohen-Macaulay. If R is a Cohen-Macaulay ring, then the polynomial ring R and the power series ring R are Cohen-Macaulay. For a non-zero divisor U in the maximal ideal of a Noetherian local ring R, R is Cohen-Macaulay if and only if ρ is Cohen-Macaulay. The quotient of a Cohen-Macaulay ring by any ideal is universally catenary. If R is a quotient of a Cohen-Macaulay ring, then the locus P spec R Rp is Cohen-Macaulay is an open subset of spec R. Let R, M, be a Noetherian local ring of embedding codimension C, meaning that C equal dim. In geometric terms, this holds for a local ring of a subgem of codimension C in a regular scheme. For R is Cohen-Macaulay if and only if it is a hypersurface ring. There is also a structure theorem for Cohen-Macaulay rings of codimension 2, the Hilbert-Bouch theorem. They are all determinantal rings, defined by the RR- of an R matrix for some R for a Noetherian local ring R, M. The following are equivalent. 1. R is Cohen-Macaulay. 2. For every parameter ideal Q an ideal generated by a system of parameters, length Riccic the Hilbert's a mole multiplicity of Q3. For some parameter ideal Q, length Riccic. See generalized Cohen-Macaulay ring as well as Buchsbaum ring for rings that generalize this characterization. As we enter this new chapter, let's navigate the complexities of the unmixedness theorem and unravel its multifaceted nature. An ideal I of a Noetherian ring is called unmixed in height if the height of I is equal to the height of every associated prime P of I. This is stronger than saying that I is equidimensional, see below. The unmixedness theorem is said to hold for the ring if every ideal I generated by a number of elements equal to its height is unmixed. A Noetherian ring is Cohen-Macaulay if and only if the unmixedness theorem holds for it. The unmixed theorem applies in particular to the zero ideal, an ideal generated by zero elements, and thus it says a Cohen-Macaulay ring is an equidimensional ring. In fact, in a strong sense, there is no embedded component and each component has the same codimension. See also, quasi-unmixed ring, a ring in which the unmixed theorem holds for integral closure of an ideal. Now, let's shift our focus to counterexamples and embark on an intellectual exploration of its various dimensions. 1. If Kelvin is a field, then the ring R equal coxdexy, the coordinate ring of a line with an embedded point, is not Cohen-Macaulay. This follows, for example, by miracle flatness, R is finite over the polynomial ring A equal K with degree 1 over points of the affine line speckle with Y0, but with degree 2 over the point Y equals 0 because the K vector space Cox has dimension 2. 2. If Kelvin is a field, then the ring chi is the coordinate ring of the union of a line and a plane is reduced, but not equidimensional, and hence not Cohen-Macaulay. Taking the quotient by the non-zero divisor X as gives the previous example. 3. If Kelvin is a field, then the ring R equal quails X, the coordinate ring of the union of two planes meeting in a point, is reduced and equidimensional, but not Cohen-Macaulay. To prove that, one can use Harshorne's connectedness theorem. If R is a Cohen-Macaulay local ring of dimension at least 2, then spec R minus its closed point is connected. The Sega product of two Cohen-Macaulay rings need not be Cohen-Macaulay. As we enter this new phase, let's uncover the impact of Grothendieck duality on our broader topic. One meaning of the Cohen-Macaulay condition can be seen in coherent duality theory. A variety or scheme X is Cohen-Macaulay if the dualizing complex, which a priori lies in the derived category of sheaves on X, is represented by a single sheaf. The stronger property of being Gorenstein means that this sheaf is a line bundle. In particular, every regular scheme is Gorenstein. Thus the statement of duality theorems such as said duality or Grothendieck local duality for Gorenstein or Cohen-Macaulay schemes retain some of the simplicity of what happens for regular schemes or smooth varieties. I'm here to provide you with the best information, so let me know what else you'd like to learn about.